I'll be talking about PSyclone existing applications. So this presentation is slightly different from what we've done so far. I work for the Bureau of Metrology and I've used PSyclone in 2 real-world applications, and will introduce you how I converted those applications to use PSyclone. They're basically 2 sections. The first very short section is using the NEMO API for a different program. So that's actually following the evolution approach. So I'm creating a hybrid version of Ocean Cold ROMs. And in the second larger part, I'll show how I ported the whole application to use PSyclone in the revolution way. So basically, I refactored the whole application. So this is a recap about the NEMO API. So the idea is that this is evolution. So you take an existing program and you convert it to use PSyclone. Automatically detects kernel, and you might remember that it's based on a very strict coding style, especially the usage of loop variables. So for example, a loop with a JK always indicates a loop's over level. There's no infrastructure involved, so whatever the application is already using for communication is what will be used. We're not introducing anything new there. So in this case, NEMO provides distributed memory functionality already. And then once we have the kernels identified, we use PSyclone only to transform the kernels, optimize them, or add additional OpenMP parallelization. Now, it was pointed out maybe once or twice that there's a config file. Now, the config file contains setting for PSyclone. It's read at startup, and a default version of this is installed when you install PSyclone. But you can actually copy this file and have a different configuration file for each of your projects. There is that's actually a typo, I just realized this. It's called --config command line option. It allows you to specify which config file to use. Now, the config file has different sections. They're very obvious to detect. There's a default section that has generic settings for all APIs. And then it has just different sections one for each API. And you actually only need to supply the one that you are using. So if you have a code that only uses, say, NEMO API, you can remove everything else to make it a bit more easier to understand. Now, if you look at the NEMO section in this config file, it actually defines at this stage which loop variables indicates which loop type. So for example, you can see here, there's this levels. Levels is indicated by a loop variable called JK, and it has a start and a stop value. Now, these are actually used in case that you got an implicit loop, like an array expression, and we need to convert it into an explicit loop. At the bottom, there's a second category, index order, which actually specifies in which order the loops should be created. You can see the yellow levels here matches with these levels. So there must be a one-on-one match. Levels is here, latitude is here, and longitude is here. There are also other loops, for example, tracers, which goes or use a variable called JT, and unknown, basically everything else. Now, there is a start and stop defined here. They are not used to detect any kernels. So they're only used if you need to convert an implicit loop to an explicit loop. Your loops do not need to start or stop with those values. Now, this allows you to actually simply modify this config file to use your own coding conventions. So for example, here's what I did. I specified levels is using a variable K, latitude variable J, and longitude variable I. I also added other loops. So there is basically grid and grid 2 using NP and MP. And then what's called sources. So those are the loops I indicated to PSyclone, and it should detect and give me back as a kernel. Once I've done this, I could then have loops, for example, like this, do J, something to something, do I, then an expression here, or in a different source file, do NP, and then other values. So basically, with a simple change in a config file, I can use the NEMO API for completely different code. Now, what's the outcome? I then basically wrote a script which is kind of similar to the script you have used in the exercise today to apply OpenMP parallelization to code. It is rather sophisticated, so it automatically not only applies OpenMP, it also tries to create parallel regions that are as large as possible. So it combines code automatically in there and is very generic. Basically, I had one application or one transformation script written and converted any function that ROMs used in OpenMP. Now, in theory, I had to hand code, in reality, I had to hand code 1 or 2 versions where just me as a computation scientist, so okay, this use, for example, should use schedule dynamic because the loop, work in this loop is just not constant enough. Now, ROMs originally supports MPI or OpenMP already, but it does not support a hybrid, so MPI and OpenMP at the same time. So I use the above script and that's the highlights here at the bottom. So one notes, adding OpenMP always makes the application slower because the OpenMP runtime library that's being linked in has use logs and there's more overhead involved. Still, we get roughly the same performance. Once you start using 4 threads, we actually get slightly faster. But we also get a good scalability. When we went up to 24 nodes, each one with 24 cores, the original ROMs was running 140 seconds. PSyclone with the PSyclone version with 4 threads was running in less than 130 seconds. So I don't know, around 8% speed up. And that's basically all with one script and the 2 variations of it. Now, the other approach is using the revolution one. Now, I'm in a somewhat bad position here because we have an additional API that has not, might have been mentioned, but has not really been introduced. And I have around 20 odd minutes to run through this, explain this other API and the infrastructure library and everything. The details are obviously way too involved to explain them here, but I want to basically show you how I did a step-by-step change or refactoration of an existing program to use PSyclone, to really PSyclone kernels and optimize an OpenMP with PSyclone transformations. So this complete port involves using an infrastructure library that is supported by PSyclone. So the infrastructure library basically gives us a communication layer and a field type, so basically a replacement of an array. I refactored the actual computations into PSyclone kernels and removed the loops because PSyclone will create the loops for you. And then I use Invoke to actually do the calls. Now the code that I used is Noah's MOS method of splitting tsunamis, and I completely rewritten this. Now MOS is a well-known example at the Bureau. We use this for many tests. We have an optimized version in C of it. So at the end, we can actually see, okay, how does the refactored version of PSyclone compare with a hand optimized version in C? Now, the infrastructure library we're using is called the Deasbury Laboratory Earth System Modeling Infrastructure Library, DLESMINF. So it's a special library for ocean codes. It has some specific settings that are typically in ocean applications, for example, staggered fields. And the only thing we're adding is OpenMP to the application. MPI is still work in progress, and it's using what's called the GeoCean API. Now, how did I start converting this application, which was pretty horrible for them to begin with, into something else? Now, basics. Obviously, you need at least one reproducible test case. All the steps I've done should each not change the results. So I was constantly running after each modification, run a test case, make sure I did not introduce an error. Then the first thing I did is I cleaned up the Fortran. Now, I said it was pretty horrible code. It contained everything from computed goto, arithmetic, ifs, common blocks. So I got rid of all of this and just cleaned up the Fortran code to be what I could call proper Fortran nowadays. I also converted all those functions into modules to automatically get a proper interface for the subroutines. Now, one very important point, I had to refactor the code to use assumed shape arrays. So basically anything with dimension : : The reason for this is that later when we introduce the infrastructure with its field type, this might actually slightly change the array sizes to align the arrays better, which means if you declare array to have a fixed size, n by m, the size will actually be wrong the moment you use the infrastructure library. So make sure you use the assumed shape arrays with the colon notation. So then I had to create proper kernels. So remember, a kernel is something that can be parallelized and it works on a single element. So it's basically, it's a 2D code. So we have a do-j loop, do-I loop, then an assignment to a field and a function. It depends on potentially I, j, and some other fields. So the actual kernel is the line in here. That's basically for a single point and should not have any dependencies to other loop iterations. So that's one thing I had to look out for. for example, in one loop, I had a code like this, do I, whatever, and then if I is less than the maximum, it assigns to DW2. Now this means in the last operation, DW2 gets not assigned and it keeps the value from the previous iteration. Now we can't have this because we can't parallelize a loop like this anymore. So I had to rewrite this loop and get rid of this dependency from one loop iteration to the next. There were also some dependencies I needed to take care of. So the code actually started with a do j, the outer loop, and had the inner loop do I to compute qw, then a second inner loop which compute qi depending on qw. Now the first idea you can see is, okay, I can easily convert this into a kernel by just removing this loop, and then I have a nested loop here and everything is fine. But you need to take care of the loop dependencies if you try this, right? In the original loop, when we use the qw here in this expression, all the qw's were the newly computed value, especially qw I plus 1. Now, the moment I basically just merged or fused those two loops, suddenly qi I plus 1 would be the next value. So I needed to make sure that in this case, I actually needed to split those two loops into two separate kernels. So the first kernel here, do j, do I, which computes all the qw. And in the second loop, do j, do I, which then uses those qw I minus 1, I, and I plus 1. So I had to use them into two kernels, and I also had to make sure this is qw was a two-dimensional array. The next step, once I had this, and remember, after every single change, I rerun my test case to make sure I still got the same results. I introduce the infrastructure library. So it's an infrastructure library for two-dimensional grids. Three-dimensional grids is planned for the future. Now it supports various grid types. Now I have to admit I'm not an expert in ocean codes, but it basically supports the Arakawa B and C grids. There are different grid types defined there. At this stage, it only supports two-dimensional grids with different boundary conditions, and it has different staggering of fields. Now the staggering of fields means certain field or the values of certain fields is between other values. And again, people in the ocean domain will be very familiar with this. The GOcean, the DLESM library actually supports and can specify a type for each field, and then it will know how the grids are staggered. So the next step was then actually to replace all the Fortran arrays with the field type from DLESM-inf. I put the URL for the GitHub repository where you can download this library, which has all the documentation in it. Now, in order to create a field, we needed to first initialize the library. Now, unfortunately, this is a little bit rushed, but basically what you need to do is you import the grid, the parallel mod, you create a grid type here. It needs to be a target because all the fields will actually keep a pointer to that grid. You call it parallel init, which just sets up the parallel system. Once you have MPI, this will call MPI init. Then we create the grid. As I said, we're already planning for three-dimensional grids, so we have actually three boundary conditions, but the third one is set to none. And the offset actually specifies in which direction of the point are the actual values, are the southwest, southeast, and that's for the staggering of the fields. Now, once we have done this, we decompose this grid, so we specify the number of points in X and Y directions, and then the number of domains, or the number of domains in X and Y direction. Those are optional parameters. It tries to do as square as possible domain decomposition, and you specify halo width. Once you've done this, you initialize the grid with dx dy, being the distance between the points. After you've done those steps, you now have a grid type. Basically, at this stage, I haven't really changed anything in application, except I get something initialized, print a few messages, and that's all. Now, the next step was then to change the data structures. So I will replace every 2D array with a field from the library. So to create a field, I create a variable field mod, and then I create a field here. I import it, including the points, and this specifies the staggering where the values are. Then I created a field, basically saying it's an R2D field for this grid, and given that this type of points for staggering. Now, then, when I wanted to use this field, so remember, before we've done this transformation, we always had two-dimensional arrays. You basically use %data, as indicated here, to get access to the actual 2D field that is part of each grid. So for example, if you have a kernel, do j, do I, you replace the access dA ij with the a%data ij. Or you can use it ua %data equals 0, or read some values in from a file. So at this stage, I basically went through one field at a time, replaced one field, make sure the results are still the same as they were before, and then started to work on the next field. Now, one caveat here is creating a field is more expensive than a 2D Fortran array, especially for temporary fields that you might create in an application. Quite often, you just declare them in a subroutine. You've got a temporary array of a certain size, and it's very quick because all that the compiler needs to do is adjust the stack pointer, set up a few minor values, and then you have your array ready to be used. The moment you're using a field, it actually calls allocate statement. Allocate needs logs in case that you're threaded. So you get a lot of overhead there. The PsyData, the DLM library actually also initializes the fields for you, which you might not even need to for temporary fields. So be aware that those temporary fields creation is more expensive. What I actually did in my application was I put it all in a module. I initialized this module, which created all the temporary fields that I would use later as a module variable. And then I had the actual computation. It didn't need to create any of those temporary fields. It was just using the ones that had been created previously. And then the next step was to actually use PSyclone. Now, I had already changed my code to have the kernel structure. So all I needed to do is take the first kernel and convert it. So that means I moved the actual computation, the computation of a single element in this kernel, into a module in one subroutine. Now, similar to what you had to do in LFRic, I needed to add a metadata declaration because PSyclone needs to know how does this kernel work, what are the array bounds for this kernel. The subroutine takes two additional parameters, I and j, which is the index, and the fields are passed as simple 2D Fortran arrays. So what does this look like in practice? So this is the metadata information, and I can only go through this very quick. It's all documented in our user guide if you're interested in a 2D finite difference code. So very similar to the LFRic API, you declare the arguments. In this case, dimension 3, meaning this kernel takes 3 arguments. The first argument is read only, and we have a stencil access to this kernel. So the stencil access in the Geocean API is actually very visual. It's 3 values. And you can see the element is the one in the middle, and it indicates how many values you go to the left, to the right, up or down. So in this case, you have a stencil access that goes one element left, right, up and down. You can specify any values here that you want. So it's I would strongly recommend to write it like this because it makes it very easy to see what's happening. Now the next argument, the second one, is read-write. So it's being read and written as well, and is point-wise. So it does not have a stencil access. And the last argument is point-wise as well. This C is again the type of field which has to do with the staggering. I didn't need this at all for my application, so for me it's all the T type. Now the other important thing that you need to specify is, remember, the loops are gone. PSyclone needs to know what are the loop boundaries. So you need to specify what elements of this array is iterating over. So in this case, it's set to internal points, so meaning it's only handling internal points, nothing on the boundary region around this kernel. And then it contains a procedure pointer here to the actual code. Now for iteration spaces, 2 interesting things. So the iteration spaces specify the loop boundaries that PSyclone will be using to create the loops for you. There are 2 implemented by default. The geo internal points is basically the inside points of a field, excluding the boundary, and then geo all points, that's inside plus the boundary region around it. Now, my application was really a bit special. I needed some additional iteration spaces. So for example, I needed 1 iteration space that would handle all the inner points and the north and south boundary, but not west-east. And similar, I had one as well. Now we extended the config file that you can now specify and define your own iteration spaces. So in this case, I added a setting here, iteration spaces. I called it internal and north-south halo. And I basically had first start -1. So start is whatever the DLSM library defines as a start point, but -1 takes me out to the boundary. And stop is the end of the internal area, but +1, so I get the outside boundary as well. Remember, at the very beginning, when we initialized the grid, we actually specified that we have a one element boundary region. If you have 2 elements, you would have a -2 and +2 here. And then for west-east, we just had start and stop, which are the inner points. This is also why I pointed out at the beginning that you can copy your config file in your application and modify it, because in other applications, you will not need this iteration space. So you would not want to add all of those iteration spaces to a global config file that you're using. Now, what does the actual kernel then look like? Well, it's the pointer we have set in the metadata to SWLon adjust code. It takes 2 additional parameters. The first one, ing, which specifies the element to use, and then all those fields. Now, well, actually, I should say arrays here, because what PSyclone passes in are actually Fortran arrays. So PSyclone knows how the DL ESM infrastructure defines the fields and only passes normal Fortran arrays to your implementation. That means you actually don't need anything of the infrastructure library to compile or understand this code. So you then declare the variables ig as integer, all the other ones as 2-dimensional fields. Remember, very important to have them as with the quality notation, even though you might know it's the sizes, because the fields created by the infrastructure library might have also actually will have a different size, slightly larger, to allow for proper alignment. And then you add a computation for a single element. So I just wrote a very dummy stencil here, which adds it, and is actually the stencil specified before. Remember, one element up, down, left, right, and we have this here, left, right, up, down, and then the center element. And then in the actual application, I removed the loops and replaced it with a simple invoke statement. So basically added a use statement from this swlon adjust module. I imported swlon adjust function, then do a call invoke. I gave it a name, time step, and then the function with the 3 parameters. So remember, PSyclone will add the loops around this and add the parameters I and j to indicate the element. And then I invoked PSyclone as part of my make file. So output for the algorithm file, output for the Psy layer, the API I selected here is version 1.0. Script is optional. Initially, I would not use any script because I was not optimizing it yet. I was just doing a one-on-one recreation of what was there. And then the file, and I built the application. And again, it was very important after each step to be able to rerun my test case and make sure I was still getting the same results. At this stage, nothing is done to the code that's changed the results. Yes, we modified the data structure somehow that stores the arrays, but this should all be taken care of. And then the first step was, the 5th step was actually to optimize and parallelize the application. So I wrote a script that optimized and parallelized the codes or use PsyData for functionality like profiling. You have seen the OpenMP code that's been added. It's very similar. This MOS code is actually very small, so I had only 6 kernels, and just basically the optimization script or transformation script that handled it was hand-coded to work on those. So this is the URL that we can read all the details about the GOcean API if you're interested in this. And I noticed a bit late on Slack that someone is actually interested in Ocean applications. So very quick in the last 5 minutes summary. So the original code was running in 111 seconds with the Intel compiler. Once I started to refactoring the kernel, it was running horrendously. Now the reason is it had really bad memory accesses, and it did strange thing with transposing arrays to make them adjacent in memory. But once I went back to PSyclone to clean up the code, and several arrays were changed from 1-dimensional to 2-dimensional for the data dependencies, as you've seen before, the code was actually running more than twice as fast as it was before. I did some other tests that had no impact. Now, this is pretty much exactly the same performance we had from the optimized C version. And I am somewhat subjective because I've written it, but I find the PSyclone code significantly easier to understand than the hand-optimized C code, because it has all the OpenMP statements in it, which you just don't see because they're all hidden in this transformation script. Very interesting, with the Cray compiler, we actually handsomely beat the optimized C version. It's always something, if I have time, I want to have a look what's actually happened there. But that was a nice result. I should put one caveat in here. The reason that we are faster, I would love to say it's PSyclone. It's mostly the code cleanup we were doing. The code was a lot simpler to handle because there were loop dependencies before that makes vectorization very difficult. So most of the performance gain is indeed caused by cleaning up the code, right? Making it a lot simpler. That's something you need to be aware of. Because of the way you have to write kernels, you're actually forced to write rather simple code, and that makes it easier for the compiler to optimize. Still, the parallelization and optimization was done by PSyclone, but in a way that's completely independent from the code now. So the outcome is that due to the refactoring using PSyclone, the code is a lot easier to understand and better for the compiler to optimize. The runtime is much better than the original code, but as I said, I can't say that PSyclone is the reason for this. It's mostly the cleanup that we did. But we have a much simpler code, much easier to understand, and you have the same performance as the hand-optimized code. That's true for the OpenMP performance that we've done as well. And in the future, we're looking at basically taking the same code base without modification and porting it to distributed memory, MPI, and hopefully even GPU code. So summary, the 2 points, the NEMO API allows you to work with existing code and can modify the config file to make it work for the code and the coding structure that you are using. Secondly, the PSyclone support for this DLESRM infrastructure library allows you to easily refactor existing two-dimensional code to use PSyclone. Always do a clean up, refactor the code to create real kernels, introduce the fields, and then create kernels, and at the last step, optimize that. Okay, that was a bit of a tour de force through the Geocean API. So my apologies. You see NEMO API had 4 or 5 hours or so all in all to be introduced. We didn't have time to run through this, even though from my point of view and my background, working for the Bureau of Metrology is actually a very interesting API that we have there. Okay, thank you very much. Are there any questions?
Thanks, Jörg. Yes, there is one question on the Google Docs, which I had up. I'll put it down. Oh yeah, Yulia asks, she says, it was interesting to see your experience with refactoring an existing code. How long did you work on it for? How long did it take? I think is what she's asking.
It took a while. For me at that time, the problem was I was starting. So I was just been introduced to PSyclone. I never used it before. I read about it. I read the transformation. I've attended some of Andy's and Rupert's presentations at the meeting. I was very intrigued. The cleanup code was, as I said, the code is reasonably small, a few thousand lines, was a few days to make the code cleaner. Introducing the first kernel took probably took several hours. So I needed to read up the metadata, how does it actually work? We didn't have that nice stencil definition at the time. I needed to work out how the infrastructure library works. So there's an initial hurdle, a few hours, probably a day. But once I had the first kernel converted, the rest was actually very quick. So basically you use the template from another kernel, you declare the parameters, you copy the code that computes a single element into the subroutine, and then you remove the loops and then test it again. So once I had this done, it was very quick. Also, what surprised me, I had an OpenMP parallelized version running, and as I said, it was the first time that I wrote a transformation in PSyclone with less than an hour. It was a really simple one. It's the same one you have used before, basically by OpenMP parallel do to each loop. But I had a OpenMP parallelized version running in less than 1 hour, in about 1 hour of my time, because once I had this application written, I just applied it everywhere and it just worked. The performance wasn't as good because of the constant startup and shutdown of the parallel regions that got then tuned later on. But it was surprisingly quick.